Hi, I'm Jacob Shepard, and I will be presenting on design aspects for polymer additive manufacturing of molds for composite fabrication. So there's this big growth in additive manufacturing, and there's also the secondary growth related to tools and things that are made from, not things that are made directly from additive manufacturing, but things that additive manufacturing helps in the fabrication process. So one example of this is in fabricating composite parts. The molds that are used are very costly and expensive, and they take a long time to make when they're machined out of metals. But if polymer additive manufacturing is used, you can reduce the cost of the mold as well as the lead time, which will reduce the life cycle. So this picture is an example of a wind turbine blade that the traditional mold costs about $1.5 million, and using BAM, it comes in at around $200,000. So there are several aspects of the design of the mold that you have to consider when you're using polymer additive manufacturing. Those are the working temperature of the polymer, the thermal expansion of the mold, preparation of the mold and surface finish, as well as entrapment if you're going to embed parts into it, into the composite, as well as using polymer additive manufacturing to create cores to go inside of the composites. So the first design aspect is the working temperature. A lot of composites are cured at a high temperature and pressure, up to anywhere from room temperature up to 180 degrees Celsius. And ULTEM 1010 has a glass transition temperature of 217 C. So that puts you about in the ballpark of being able to use the ULTEM as a core in a heated curing cycle of a composite. But it can also be used for non-heated curing cycles. And then another thing to keep in mind is that heat is generated as the resin cures in the composite. So one paper showed an example of their polymer, their ABS mold that they had made, and they had machined it. And then after curing their fiberglass composite, they had an imprint of the fiberglass pattern on their mold. And so that's something that you have to take into account as you are designing. Another factor is the thermal expansion. If you're heating the mold, you can have a mismatch in the coefficient of thermal expansion between the composite and the polymer mold. So if your mold is shaped as a female part where your composite is inside, that expansion and contraction could trap your part inside of the mold. So a better approach would be to create a mandrel or a male molded piece. And then you can actually use that expansion to your benefit by the expanding polymer will add pressure to your composite layers and help to consolidate them. So there's a lot that goes into the preparation of the mold and the surface finish. If the surface finish is a concern, some applications, the composite needs to have a rough surface, or it isn't as big of a concern. But where it is, there's a couple of different approaches that researchers have taken. One is to use commercial epoxies to coat the part, and then those coatings were sanded and polished. And some of them, so they use some with an adhesion promoter on the polymer mold before they put the coatings on, but those only lasted for making one part, and then the coating came off. And then with some of the other coatings, they used the adhesion promoter, and they were able to make 1 to 4 different parts out of that same mold before the coating was damaged to the point that it wasn't usable. So here's an example of that damage that they get. The top one is considered an adhesive failure, and that's where the coating pulls completely away from the mold. And the bottom one is considered a cohesion failure, where the coating comes apart from itself. and you're left with kind of spots without coating, and it becomes uneven, and depending on your application, it may or may not be able to be used at that point. Those same researchers also took a curved part and with a little bit more detail, and they machined it to get a relatively smooth surface. And they found that the orientation that the part was printed in and the angle that they were machining, they would have different surface defects just based off of the angle. And because this was used in BAM, it was oval roads that were being laid down. And then they also used a ferro arm to measure before and after, so they could compare the deviation of the surface as they pulled parts off of it. So here's some pictures of the buildup on the mold. So this is composite material. This white area is the composite material building up on the mold. And then these pictures on the right are the carbon fibers from and the ABS, the carbon fiber ABS mold that was sticking to the composite part. So the more times they used it, the more likely they were to get that carbon fiber ABS stuck to the composite part. So entrapment is the idea of having parts embedded into your composite, and you need to account for the shape of the part, and you also have to be able to get the mold out. So one way to do that is by using a soluble polymer such as HIPS. So this picture is a great example of the process where you design your part in CAD, you use your HIPS, you print it out, and then you embed your sensor or whatever it is. Then you cast your composite, and then you dissolve the HIPS, and then you end up with your final sample. So one factor here is the being able to accurately control the shape of the mold for where your embedded device is going to go. So in this, they used a camera to print out a test pattern to figure out the errors. There's two errors associated with material extrusion, the position and then material shrinkage. And so by doing this testing, they were able to modify the original geometry that they printed so that it came out accurate. And the last approach or design consideration is having polymer additive manufactured cores inside of your composite sandwich. And this adds stiffness, and you can also control where the material is within the core. So a couple of studies were done on this, and one used ABS cores, and they found that the density of the cores didn't have a significant effect on the strength and modulus of the part, but the number of layers of composite material that they applied to the outside did. So this picture on the right shows the process of building it up, and then here is a picture of the fracture of it. And then there was another test done where instead of comparing different core densities, they tested a flat core as well as a corrugated core. That's what this bacon-looking image is down here. Is the corrugated core is a wavy feature, and they also experimented with different materials and different additive manufacturing processes. So they had epoxy with SLA, ABS for material extrusion, and the plaster powder for binder jet. And they showed from all their testing that the corrugated geometry always came out stronger, and the SLA epoxy was a stronger core than all the others. And they tested this using a bending test. So in conclusion, polymer additive manufacturing can be used to help reduce the fabrication costs of composites and their timeline, but certain aspects need to be kept in mind as discussed. And those are my references. How do I stop recording?